Okay, I would like to start with a few different activities. I want you to number your paper 1 through 4. The first thing that I'd like for you to do is to assign a letter, uh, A, B, C, or D, according to the following. If you walked to school today, I want you to write down the letter A. If you rode your bike to school today, I want you to write down the letter B. If you drove or rode in a vehicle today, I want you to write down the letter C. And finally, if you got to school another way, I want you to write down the letter D. For number 2, I want you to assign yourself either E or F. If it took you fewer than 10 minutes to get to school today, write down the letter E. If it took you more than 10 minutes to get to school today, write down the letter F. Now I want you to assign yourself G, H, I, or J. For number 3, if you're wearing blue today, write down the letter G. If you're wearing red today, write down the letter H. If you're wearing black today, write down the letter I. If you're wearing white today, write down the letter J. Now I'd like you to assign yourself K, L, M, or N. If you were born in January, write down the letter K. If you were born in February, write down the letter L. If you were born in March, write down the letter M. If you were born in April, write down the letter N. What was different about these 4 sets of instructions? Think about that a minute. Pause your video, and when you're ready, press play again. Well, you should have realized that for the first 2 assignments, it was really obvious what letter to pick. But when you got to the third, what if you weren't wearing blue, red, black, or white? What letter did you give yourself? What if you were wearing blue and red? Then what letter did you pick? That's a problem. For number 4, what if you were born in May? What letter did you give yourself? That's an issue as well. So when you are making assignments, certainty is important. We have a special name for this in mathematics, and that is the subject of Chapter 3, functions. First, let's define a relation before we talk about functions. A function is a special kind of relation. A relation is the correspondence between 2 sets where each element in the first set, called the domain, corresponds to at least one element in the second set, called the range. All of the instructions that assign you to letters were relations. All of the students in our class were the domain, and the letters assigned were the range. Now, you should be making sure that you're taking notes, and if at any point you need to pause the video so that you can finish, please do so. Now, a function is a special kind of relationship. It is a correspondence between 2 sets where each element in the first set, called the domain, corresponds to exactly one element in the second set, called the range. So our assignments are very clear. We know exactly, if we have an x value, what that y value is. Which of the sets of instructions assigning you to letters were functions? Press pause, and when you're ready, press play for the answers. Number 1 and number 2, I believe, were functions. Let's go back and look. Number 1, every single person in here should have been assigned a letter A, B, C, or D, and they did not overlap. No one should assign themselves 2 letters at once, so that is a function. The second one was also a function. If it took 10 minutes or less or 10 minutes or more, they did not overlap and everyone was assigned something. However, number 3 was not, because you could have worn blue and red and then not known what letter to assign. So you would have assigned more than one letter for wearing 2 different colors. in addition, maybe you weren't wearing any of these colors and then there was no assignment at all. Same thing with K, L, M, and N for number 4. January, February, March all had assignments, but after that, no letters were assigned. So number 4 is not a function either. Now, here are 2 different diagrams of relations. And I have the domain on the left rectangle and the range in the right rectangle for both of these. Now, the question is, can you tell whether each is a function, and how can you tell? Press pause, and when you're ready to hear the answer, press play again. The answer is that the first one is a function. That is because every element in the domain, the first set, is assigned to exactly one element in the second set. One arrow out of each element in the domain. Let's write that down. Arrow out. Okay. The second one is not a function. And that is because 7 p.m. is assigned to 2 different places. So we have more than one arrow out, and it is not a function. Relations and functions between 2 quantities can be represented in many ways, including mapping diagrams, which is what we just saw, ordered pairs, equations, graphs, and verbal descriptions. So far we've seen the verbal descriptions, that was in the beginning activity, and we saw mapping diagrams. That was in the last screen. Now, the next function, well, the next relation at least that I show, is a set of ordered pairs. Every x value is assigned to a y value. And this is a function because every single x goes to exactly one y. The x component of each ordered pair is listed only once. Okay, so that's how you can tell from a set of ordered pairs that it's a function. The x component is listed only one time. What is the domain of f? The domain are all my x values. It is the set of all possible x values. And we write it with set notation, -3, 2, 3, and 6. What is the range? The range is the set of all the y values. And my y values are 4. 4 is repeated here, and 5. So the domain is a set, and the range is a set. The domain is the set of all x. The range is the set of all y. Now, functions and relations, for that matter, can be described using equations. And what's nice about this is there are infinitely many points that I can create from this equation. You don't have to list all the ordered pairs. So I have some x values in the left column, and I calculated the y values in the right column. And of course, there are a lot more y's that I could create based upon any value that is in my domain. Now, some equations represent functions, whereas others do not. The equations on the left are functions. Every x is assigned to exactly one y value. However, these equations are not functions, and let me show you why. If we look at this one and we solve it for y is equal to plus or minus the square root of x. So for every x value, there are two y values, not a function. In this case, if I solve for y, I'd get y squared equals 1 minus x squared. And if I took the square root, I'd have plus or minus the square root of 1 minus x squared. Every x value is assigned more than one y value, so therefore not a function. Same kind of idea here. If I solve for y would equal the absolute value of x. Or no, not that, sorry. Let's try again. Y would equal positive x, or y would equal negative x. So there are two y values for every x value, not a function. Graphs of functions and relations. I have all the graphs here shown for the functions and relations on the previous page. Here, let me show you. So if we look at my equations that are functions, I have them here. Y equals x squared, y equals the absolute value of x, y equals x cubed. If I look at my equations that are not functions, they are here. Now, let me make that larger for you. Now, I want you to take a look at these graphs and see if you can figure out how you could tell by looking at a graph whether or not a relation is a function. Press pause on your video, and when you think you're ready to hear the answer, press play again. Well, let's look at this set here. How can you tell by looking at a graph if it represents a function? I have one up here, one down there. If I look at this one, every x value is assigned exactly one y value. However, over here, every x value is assigned two y values, and that would not be a function. We have a nice test to see if a graph represents a function, and it's called the vertical line test. A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. You can tell by looking at my top graph that no matter where I put this vertical line, I intersect my graph in exactly one point. However, if I look at this vertical line, I can find all sorts of places where my vertical line intersects the graph in two spots, so that is not a function. Function notation looks like this. It's nice if we can name our graphs, so that is the purpose of this. So f of x equals 2x plus 5. I could also name another function g of x. That way, when we're referring to our graph or referring to functions, I can say, oh, f or g, and then we're naming them. F of x represents the y value, and now what I'd like to do is evaluate f of 2. So we simply put 2 in for x. So 2 times 2 is 4, plus 5 is 9. And that is all there is to it. Now I want to evaluate g of x plus 2 and g of negative x. Now, just like I could put a number in for my function, I can put in any expression. This should be seen as a placeholder. So whatever is here is what goes in each of these boxes. So let's go ahead and do that. G of x equals x plus 2 squared minus 3 times x plus 2. You'll notice all I did was replace each of these with x plus 2. So now we're going to simplify. So I'm going to multiply out x plus 2's quantity squared, so that's x squared plus 4x plus 4. We'll distribute in the 3, minus 3x minus 6. Now we'll combine like terms. 4x minus 3x is just plus x. 4 minus 6 minus 2. Now, could I factor this? Well, yes, of course I could factor it. Is it necessary? No, because this form and the factored form, both of them are just as simplified as the other. So I would leave it like this. Now, g of negative x, I'm going to do the same kind of thing. Except, let's see if I can erase this now. Instead of putting in x plus 2, I'm going to put in negative x. And again, this is just a placeholder. So we're going to put in a negative x anywhere there's an x in my function. So that becomes minus x squared minus 3 times minus x. Notice that the negative is squared here. So now we're going to simplify. That becomes x squared minus a negative 3x. That would be plus 3x. And there you have it. Now, I can evaluate sums of functions. I have h of x plus h of 1. So we'll find h of 1 just by substituting 1 in for x. So that'd be 1 plus 2 or 3. So when I evaluate this, I'm still going to have my h of x, which is x squared plus 2x, and then plus 3. Could I factor that? Well, no, it doesn't factor. But even if I could, there really would be no reason because it is as simplified as it can be. Now, I want you to take a minute and I want you to evaluate h of a half and h of 1 over h of 2. Press pause when you're ready to see the answers. Press play. And here are the answers. I have h of a half. We're just plugging in half for each of the x values there. And then I have h of 1. I plugged in 1 into h of x. And I plugged in 2 to get h of 2 down here. And I simplified. Notice how these two values are different. H of 1 over h of 2 is different than h of a half. And that would be our lesson for today. So what did we learn? We learned about what functions were and what they were not. When it's a function, every single x value has exactly one y value. Let's get back to where that says. Every x value has exactly one y value. We learned about the vertical line test. You can look at a graph and tell if it's a function based upon if my line intersects my function in more than one spot. Here we go. We talked about how to tell if a set of ordered pairs was a function, and that is when each x value is listed no more than one time. The domain is a set, the range is a set, and we also learned that when I look at an equation, I can tell whether or not it's a function. If it's a function, every x value is assigned to exactly one y value. And right now, what I'd like you to do is do the assignment on Schoology, and I will see you tomorrow. Have a wonderful day.